Chapter 4, Integer Programming. Okay. Integer programming is essentially the same as linear programming problem, but the solution required here are integers. Like when we say some factory want to produce products, cars, for example, and then we want to see how many cars per day and so on. It does not make sense to say we want to manufacture, for example, 4.5 cars per day or per hour. It does not make sense, right? So some linear programming problems requires the solutions to have integer values. In such a case, we will call them integer programming. Okay. What we do in this lecture, we will just explore some kinds of integer programming. So the integer programming in which the variables must assume only integer values. In this chapter, we formulate a number of problems that require integer variables and present three algorithms for solving them. Okay. Now, all what we want to do in this section 4.1 is to go through four kinds of such examples of integer programming. Okay, the transportation problem. Okay, what is that? The transportation problem. The idea here is some company have some factories and some warehouses, factories. And warehouses. Okay. Now احنا بنعرف الشركة عندها مصانع وعندها معارض للبيع. فعندها مصانع it has factories in city A, city B, C, D, okay, distributed all around the world maybe or the country. ومعارض البيع warehouses distributed in some other places, maybe same cities, maybe different cities of the factories. Now, moving the product from the factory to a warehouse, it has some cost. So it might be better, for example, this warehouse to receive products from this factory, that and that only, and the other warehouse to receive from this and that, and so on. So the question, how we do this distribution from factories to warehouses so that we minimize the cost of shipping, of distribution. Okay, now let's take some notations here. Assume we have M factories and N warehouses. Okay. Now, shall we give them notation? Maybe factories, let me say, okay, factory 1, factory 2, and factory I till we reach factory number M, and warehouse 1, warehouse 2, and warehouse, let me say J, till we reach some warehouse N. Okay, now the idea here is the cost of shipping from factory 1 to W1, we will call it C11. From factory 1 to W2, we will call it cost 1, 2, and so on. From factory 1 to WJ, it will be cost 1J, and so on. Okay? Now, in general, from factory I to warehouse J, the cost is CIJ. And this is what we are saying here. So the cost of shipping from one unit from the ith factory to the jth warehouse is CIJ. Good? Now, our problem is to determine the amount. Okay, we did not now say what is Xij. Now we are saying that the cost C11, C12, C1J, Cij the cost of shipping one unit. Maybe you will ship like 1,000 units or 100 units from factory to somewhere else. Each unit will cost you that much. Now we want to know how much units we shall send from factory I to warehouse G so that we minimize the cost. So we need to know the number of units that being sent from factory I to warehouse G. And let's give them this amount. So amount number of units. Let me say here number of units shipped is xij. So in here it will be x11 number of units sent from factory 1 to warehouse 2, and in here it is number of units sent from factory 1 to warehouse 2. This the previous one the previous one was from factory 1 to the warehouse 1, and this is number of units sent from factory 1 to warehouse J, and so on. Okay, and apparently the cost now is this, to minimize this cost, right? The cost times number of units. Good. Okay, now let's go back here and says the demand of the warehouse J is DJ, like we are seeing here. How many units warehouse 1 wants? It wants, oops, okay, let me take this down right here. So this wants how many units? D1 units. And this wants D2 units, DJ units, DN units. And we must know also how many units each factory make. How many units each factory makes. So we will say this makes S1 units, S2 units, SI units, and then SM units. And indeed, the number of the demand, the number of units shipped, so these factories make this amount of units, and what you will ship is indeed less than that amount. So what you ship from, for example, from factory 1, which is C11 plus C12 all the way to C1N, this indeed must be less than or equal what that factory makes. Good. And now this applies for every J. So if instead of having I1 in here, so we say J from factory J to warehouse 1, factory J to warehouse 2, factory J to warehouse. Let me call it I, sorry, let me use I. Because we just denoted the number of factories with I, right? So the factory I from warehouse 1 to warehouse 1, factory I to warehouse 2, factory I to warehouse N must be less than what factory I makes. Okay, good. Okay, now if we make this run as J, we can write this actually, let me say we can write this as the following, just rewrite the summation of Ci. Now I is fixed here, J is moving, J from 1 to N must be less than or equal Si. So I is fixed here. J is moving. Good? Okay. Now, what about the amount that WJ receives? The amount that this warehouse receives. It needs no more than DJ, but it receives from factory 1, factory 2, factory 3, and so on. Right? I did a mistake in here. Maybe you fixed somebody or the notice fixed me. No, this we were talking here about amounts, so not cost. So these are x's, not c's. Sorry, I shall be looking at the x's in here, but the colors confused me. Okay, amounts. The amounts we are shipping are the x's. Okay, now uh, let me say. Let me go back in here and write the units that factory I the unit that factory I sent, or the units that are sent, the units that are shipped from factory I. This is what I'm talking about. Okay, so the units that are shipped from factory I must be indeed less than what factory I makes. Now, what about the units that warehouse J receives? So let me write that. The number of units that the warehouse J receives. So warehouse J receives from uh, factory 1 and also receives from factory 2 and so on till we reach factory M. Okay? And what it receives, it must be greater than or equal its demand, right? You cannot send less than its demand. You must send greater than or equal. So this can be written as x I j here is fixed, okay, and now I is moving from 1 to m. That must be greater than or equal dj, and therefore we got these constraints that apply for j fixed at a time, but j sometimes it is warehouse 1 or warehouse 2 or 3 till we reach the warehouse number n. And for this, I is fixed, but I equals sometimes factory 1 or factory 2 and till factor n, because this applies for every one of these. So these are the constraints. Okay. Now, this problem is converted to standard form. Then the only entries in the constraint matrix are 1, -1, and zeros, right? Do you agree? The ones and negative ones and zeros, right? Because each x represents the amount uh, that we ship. So the coefficient will be 1. A -1 because we might need to introduce the slack variables. Because of this, the slack variables will have a coefficient -1. And zeros may be because some xij may not appear. Maybe you will not send anything from factory 3 to warehouse 5. You will not send anything. So xi35 is 0. Okay, good. So the whole problem here is called the transportation problem, and this is very famous problem. Transportation problem. Very famous problem in integer programming. Okay, let's go and see the other kind of problem, which is called knapsack problem. Okay, what is talking about? Let's see. Not very famous as the first one. Consider the problem faced by a hiker who cannot carry more than K pounds. So K pounds of equipment, that this is the most, the largest weight that the hiker can carry out. And she has n items. She must take, she has n items that she is considering bringing. So she needs to choose. To each item, she assigns a relative value. Okay? يعني كل غرض معين له أهمية معينة، أعطت هذه الأهمية هذا النمبر. الغرض الأول له أهمية 5 مثلا، الغرض الثاني من 10 له أهمية 7، الغرض الرابع له أهمية 9، مهم كثير مثلا. هذا هو الترتيب. With the most important item having the highest value. Okay? Let AJ be the weight of the item. So every item has a weight. So let us say here item number I, uh, the weight, how heavy it is, AI, and let's say the value, how important it is, CI. Okay. So the hacker's problem is to decide which of the n items to carry out. She will choose those that maximize the total relative value subject to weight limitation. Okay, so the weight limitation shall not exceed k pounds, and this give us the weight. So we will not allow the weight to what? To exceed k. So it shall be less than or equal k. Now we will introduce the variables. Now some items she might take and some items she might not take. اوكي الان عندنا الاغراض مثلا A1 10 اغراض لنفترض، فعندنا الويت A1 A2 A3 to A10 ماشي الحال، لكن ما بصير نجمعهم كلهم. ليش؟ لانه بعض الاغراض ممكن ما تاخذهم اصلا، فاحنا بحاجه نحدد نعطي variable ايش؟ للغرض اللي راح تاخذه نعطيه 1، اللي ما تاخذه نعطيه 0 لاجل نلغي الوزن بتاعه. اوكي، فهذا هو ال variable. Let xj equals 1 if the jth item is chosen and xj equals 0 if the jth item is not chosen. So خليني أرجع هنا، هي استعملت j فخليني نستعمل j هنا. Okay. بناء عليه maximize the value. The value we know it is cj xj because multiply this with that and add. Now, whenever xj is 0, then we are not taking that item, then there is no value coming out of that item. And now the weight, you can compute the weight to be this. It must not exceed k. Now, if xj is 0 again, then that weight, that item is not taken, so its weight is not considered. Okay? Good. Noting that by limiting the value x to 0, 1, the left-hand side of the constraint just represents just the weight of the item. Okay, this is what I just said. It just of the weight of the item that have been chosen, where xj is 1. This type of integer programming problem is called 0, 1 programming problem. Okay, so this is another kind. The assignment problem. Okay. The assignment problem, what is it about? Okay. Suppose you have n people that are applying for J jobs using various criteria, including, okay. So let us say here we have people. We have person 1, person 2, and person n. Okay. And we have jobs. Job 1, job 2, till job n. Okay, what's about? Using various criteria including past performance, uh, aptitude, and job ability, we specify value Cij that would accrue if the ith person is given the jth job. Okay, now it says the following: if person one takes job C1, then the value, the good or bad value is C1 1. If person one takes job 2, the good value is C1 2. Now if you go back here and say, okay, this is job J, this is person I, and we keep going. If person one take the job J, then some value they have somehow based on past performance, aptitude, job ability. They just compute it somehow. 1J, and if person one take the job N, then C 1n is the value, and so on in general. If person I take job J, then the value is Cij. Okay. Okay. Now we assume that each person is assigned exactly to one job and each job goes exactly to one person. Okay. Our problem is to assign people to jobs so that the total value of the assignment is maximized. Okay, so now again we will introduce xij to be 1 if person I takes job j, and 0 if person I does not take job j. Now to maximize the value, we will multiply this. Okay, I think this is clear. This is similar to the very first one. Now, if some person does not take, if some ij is 0, that means that person I is not taking job j, then xij is, sorry, is 0. So cij is not taken because it multiplied by 0. So cij would be taken only if person I takes job j. So in this way, do that summation will give us the total value. Now, what are the constraints? The constraint here says first constraint and second constraint. If you pay attention to this one, what does it say? So it says, so j is fixed for a while. It says now I is moving. It says x. So let me explain it for person one. So x11 plus x12. What is that? Till x1n equals what? x11 is person 1 takes jobs 1, x12 is person 1 takes jobs 2, x1n is person 1 takes job n. Person 1 can take only one job. So one of these is 1 and the remaining are zeros, right? So when we add them, we get 1. Same thing applies for person 2 and person 3 and person I. So person I taking job 1, person I taking job 2, person I taking job n. But person I takes one job only. So all of these are zeros except 1. And then we get 1. This is explanation of that. Okay? I did, I did explain the second one. This is explanation of the second one. This is explanation of the second one. Sorry. Okay? This is explanation of the second one. Now, let's go back and explain the first one. First one says, okay, job 1 is taken by the first person, plus job 1 is taken by the second person, plus all the way job 1 is taken by person number n. But job one can be taken only, any job can be taken only by one person. So job one is taken only by one person. So all these x's must be zero except one of them. So add them, you get one. Now that applies for every job. So job J taken by first person, job J taken by second person, job J taken by n person, but job J is taken by only one person. So all these x's are zeros except one. So add everything, we get one. Boom. And there we go. Good. And all these is explanation what I just said, to what I wrote in there. Boom. Okay, now we will learn, this says we will learn a special algorithm to solve that problem. Okay, now the very last example, what does it say? Suppose we have a situation in which either constraint this or constraint that is happening. We can convert this condition to one in which the constraints are linear. If we have variable numbers m1 and m2 such that this is happening and this is happening for our visible solution. So the idea here is either or problem. This is says either or problem. So it says either this is happening or this is happening. So we have some values. So we have two constraints. So let me write it this way. We have some variables. This says a11 x1 plus a12 x2 plus a1n xn less than or equal some integer. Now, this is the idea here, multiplying this variable by x1. So we want solutions for these x's. Now, a11, a12, a1n are constants. So we either have this, or if we don't have this, we go and then use this again. If we don't have a solution for the above one, we might have solution for this one. Now x1, x2, till we reach xn, but less than or equal another integer. Now here, these are other integers. Just we give them these names. So we either have this or that. Okay? And actually, we can make it easy, like either, let's take a simple example, either 3x plus 2y is less than or equal 5, or 2x plus 7y less than or equal 9. Either this or that. Do you have a solution for the above one? No, yes, okay. What about the second one? Okay. Visible solution, maybe. Huh? Maybe you don't have visible solution for the first one. Maybe. We do actually. Okay. So this is the idea, but having more than two variables, we will say x1, x2, x3, x4 instead of x, y, z, w, and so on. Now, what does it say? Is we can convert this condition to one constraint. One constraint. How? If we have numbers of variable like that. Okay. So take this here and take this here, subtract. Like this amount is less than 5, right? So we might say, okay, so we have 3x plus 2y minus 5. Okay, it is less than or equal what? Less than or equal maybe negative 2. No, yes. Do we have such a thing? Maybe, yes, no, yes. Okay, if we have it, we call it m1. And here 2x plus 7y minus 9. less than or equal, do we have or we don't or we don't know? So we will call it M2. So if we have such M1 and M2 such that this is happening, then what we do to convert both of these to one equality, what we do is the following. Just try them this way. This is easy now, huh? Let y be 0, 1 variable. Okay? Now look at it. If y equals 1, this will be in hand, which gives the first inequality. Good? Now, if y equals 0, okay, let me see before that. Now, if y equals 1, we get the first inequality. But what happened to the second equality? This will be 0. It will be demolished. Good? Okay. Now, if y equals 0, then we get the second equality. So we get that one. But what happened to the first one here? It will be demolished because y is 0. Will be finished. So y equals 0 or 1. So we could convert that to convert this condition to one in which the constraints are linear. Okay, and this is what I have just explained. Okay, these are the four kind of examples for linear integer programming, and this is the first section of this chapter. We just learned what are these problems, some kinds of them, some examples, and we will learn in the two sections of this chapter some algorithms that help us to solve this kind of linear programming problem that requires for its solutions integer values. So basically, this means we will learn how to solve integer programming problem. And we are done. Thank you.